Hello and welcome. Today's lesson will focus on drawing the Lewis diagrams of ionic and molecular compounds. So to review, all the elements on the periodic table want to achieve a full octet or electron shell of valence electrons. So if you remember, the groups in the periodic table give us a sense of the number of valence electrons in the elements of that column, whereas the periods give us a sense of how many electron shells in that element. So for example, hydrogen being in the first column, the first row, has one valence electron and one electron shell. Okay, so the first electron shell for hydrogen and helium only holds 2 electrons. So in this case it's not really an octet, there's a bit of an exception here, where it likes to have two electrons to fill its octet. The second row here, the second period, from lithium all the way across to neon, this is where the octets start, and from below there, for our purposes now, we're all going to assume that they want a full octet. 8 electrons. There are some exceptions to that, and we'll run into those as they come along. It's easier for metal ions, the ones on the left-hand side of the periodic table, to lose electrons. Right? Lithium, beryllium, 1 valence electron, 2 valence electrons. Much easier to give up those electrons than to gain 6 or 7. And similarly, if you go to the right-hand side of the periodic, looking at the gases, oxygen and fluorine, they're much more inclined to gain electrons, because that's much easier to do. So there are a couple of exceptions to the octet rule. Again, we mentioned hydrogen and helium. Beryllium and boron, they like to have 2 or 3 in their valence shell, and they tend to be electron deficient in this case. If you go past period 3, they have these empty d orbitals that can hold extra electrons. And what those d orbitals look like and how all that works is something that you'll touch upon in grade 12, but it's an exception to note that, and we'll run into as we go. So the first thing we're going to touch upon now is drawing Lewis structures for ionic compounds. So to start with, we need to remember that ionic compounds are just 2 ions that have been created by giving away and accepting an electron, and then are highly attracted to each other. So we start by drawing the electron dot diagrams to represent the structure of each ion, and then balancing the charges on these ions by adding additional ions where necessary. So let's start with NaCl, our typical table salt. If we look at the periodic table, we see that sodium in the first column has 1 valence electron. So our Lewis dot diagram for sodium is very simple. We have the symbol for sodium and our single valence electron. Chlorine, we find it on the other end of the periodic table, and so it must have 7 valence electrons. Okay, and this is very obvious here now. These 2 elements want to have a stable electron shell, and so sodium is going to give up its electron and donate it to chlorine. So we end up with no valence electrons for sodium and a full stable octet for chlorine. Now an electron has been donated, so now looking at sodium, it should have 1 more proton than electrons, making it positive. So we're going to show that and illustrate that by using square brackets and just putting a positive charge outside the bracket. Same thing with chlorine. Now it has an extra negative charge, having added an electron, and so we're going to put the square brackets and a negative charge on chlorine. That's your Lewis dot diagram for an ionic compound. This does get more difficult. Looking at aluminum oxide below, we have multiple atoms, or multiple atoms of each element. Okay, so let's start basic here. We're going to look at aluminum. It has 3 valence electrons, and oxygen has 6. Okay, so now you're looking at an element in oxygen that is looking to gain 2 electrons, and an element in aluminum that's looking to lose 3. So in a direct relationship here, if I were to take 2 from aluminum and put them in with oxygen, oxygen's happy, but aluminum still needs to get rid of 1. And so you would bring another oxygen in, and it would take from aluminum, but now it's missing and it's unhappy. So you need another aluminum atom, and again, take 1 from aluminum and give it to oxygen. You still have an unhappy aluminum, and so a 3rd oxygen is needed, and these last 2 electrons from aluminum can fill oxygen. So this is where now you see why you need 2 aluminums to satisfy your 3 oxygens. And so the same rules apply as we did with sodium chloride. You draw your aluminum ion. It is both aluminums have given up their 3 electrons, so there are 0 electrons in the valence shell. There are 2 of them, however, so we're going to put a 2 in front. And it has a charge of 3+ because it's given up 3 electrons. Oxygen, on the other hand, now has its full valence shell. It is an ion, so we need square brackets. Each atom has gained 2 electrons, so it's a 2-, and there are 3 of them, so we put a 3 in front. Okay? Now, covalent compounds are a little bit more in depth. There's a little bit more to them. So now we're going to talk about sharing electrons rather than giving and taking. We're not dealing with ions anymore. We're dealing with that sharing. So the first step that we need to do when drawing these is identify the central atom. And it's the element with the greatest bonding capacity, or more often, or very often, the weakest electronegativity. Okay? So we've talked a little bit about electronegativity, and we see that for the most part we find electronegativity increases towards the right hand side and moving up to where in the periodic table, whereas the bottom left is going to have the least and the top right will have the highest electronegativity. Something like fluorine has a much higher electronegativity than anything else, and we can see that looking at the periodic table, and you can see the sort of the heat map here as you get the low electronegativities up to the high. So we can use electronegativity to help us draw our diagrams. Then we want to determine the total number of valence electron pairs available for bonding by adding up all the valence electrons of each element in the compound, and we'll have a good sense of what's happening here. So looking at carbon tetrachloride here, we need to start by figuring out what my central atom is. And you'll often find, without even looking at the periodic table, the first one listed and the one with the least number of atoms is often your bonding atom. So we can see just by looking here, chlorine 3.16 is a higher electronegativity than carbon, so carbon must be our central atom. And this is a good place to start. Now, let's look at chlorine. Chlorine has 7 valence electrons, okay, which means, and you have 4 chlorines. Okay, so you can actually figure out how many valence electrons from your chlorines. You get 7 times 4 means you have 28 valence electrons, and carbon has 4 valence electrons. So we need to account for a total of 32 valence electrons in this Lewis structure. So our next step now is to just draw a single bond from carbon to each of my chlorine atoms. And now I'm just going to fill the valence shell for all my terminal atoms, my chlorines. At this point now we just need to count up and see if I've accounted for all of my valence electrons. So I need to have 32. Each of these bonds counts for 2, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So this is my completed Lewis structure for carbon tetrachloride. Now, let's take a look at a different option here in terms of silicon dioxide. We're going to take the same approach. So our oxygen has our 3.44 electronegativity, silicon a 1.90 electronegativity. So again, silicon with the lower electronegativity is going to be my central atom. And now I'm going to add up valence electrons. Oxygen has 6, silicon has 4. So our 12 plus 4 is 16 valence electrons that I need to account for. So I've put my central atom down. Again, I'm going to draw a single bond to each of my outside atoms and fill the valence shell. Now that I've filled the valence shells for my outside atoms, I need to double check now that I have my full octet for all my atoms. So again, I'm looking at 2, 4, 6, 8 for that oxygen, 2, 4, 6, 8 for this oxygen. But when I look at silicon, I only have 2, 4. So I need to satisfy all 3 of these atoms as best I can. So to approach this, I'm going to take away 2 of my valence electrons from oxygen, and I'm going to create a double bond for silicon. And now I have 2, 4, 6, 8 around silicon, 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for that oxygen. So now I have my final molecule of silicon dioxide. Okay, so there's your covalent bonding ionic bonds, or Lewis structures. So your covalent bonding Lewis structures and your ionic bonding Lewis structures. Okay, so again, format's different. Again, because you're giving and accepting with an ionic bond, you're going to have your 2 ions formed using square brackets, where in your covalent compounds now, you're adding up those valence electrons and sharing electrons to make all the atoms happy. Thank you, gentlemen. We'll see you in class.